Hello there, welcome to lesson number 9 in our series on using FluidDesigner for 3D printing. In this lesson we're going to introduce you to using parametric equations to create a heart-shaped object. So if you start FluidDesigner up, and if I just open this panel up a little bit, we need to go to Learning Projects Objet. We're doing lesson number 9, so I will drop 09, the heart shape, onto the workspace there, and again I'll just open this panel up. So this is the object that we're going to create. It's, as you can see, it's a kind of heart-shaped object. It's pretty large. It's 140 by 185 by 200 millimeters. Okay, so if you printed it, it would be quite expensive to print at the moment, but what we're doing is we're just showing you how you can create this sort of object relatively quickly in FluidDesigner using built-in functions. And the function we're going to use is an XYZ math surface. So we're going to use 3 equations: an X equation, a Y equation, and a Z equation. So X, Y and Z, those are the 3 axes, X, Y and Z, and with 3 equations you can come up with interesting objects. So if we go to add mesh, we need to go to math function XYZ math surface. Now the initial equations that are produced are these, quite complicated ones, but if we just go to view and zoom to selected, you'll see what the current object is, and just need to move these windows around, and as you can see it's actually a shell. And if I press the tab key on the keyboard, this panel's going to disappear and we'll have to put it back on again, but if I press the tab key, you can see our shell is made up of faces. Now I will be honest with you, trying to print this is not that straightforward, because in here the faces go on and on and on and on, and you need to solidify this. You need to give it some thickness. At the moment it is not just looking like a shell, it is a shell, it's got no thickness. So when you try and thicken this up, it's a little bit awkward to actually try and print that object. Now I'm going to have to delete it because I've lost my panel here, and I'm going to have to add it again just because I went into edit mode there. So it's add mesh, math function, XYZ math surface. Now we want to create our heart-shaped object, and to do that we're going to have to use the equations that are down in the window here. So the X equation, we want to change it to cos bracket, so this is cosine from school days when you did trigonometry, 2 times V close bracket. And as you can see, that changes our shape now. So we've got a completely different shape here just by changing the X. Now if we actually change any of the values in here, these equations, things will change as well, and we'll get completely different shapes. So, you know, you could just click in here, for example, if we change that 8 down to a 2, yeah, you can see the shape changes, and if I change the other 8 down to 2, you can see the shape changes again. So, you know, you don't need to be a rocket scientist to actually change these values. Okay, I mean, you do need to know where the equations, which equations to use to start off with, and we'll show you at the end of this lesson where you can find some of those equations. But anyway, let's continue with what we're doing. We would need to change the Y equation now to sine bracket 2 times U. That's displayed here. And then finally we want a Z equation, which is a little bit more complicated. It's sine of V multiplied by bracket 2 plus cosine 2 times U, close bracket, times the sine bracket 2 times V, close bracket. Now hopefully I've typed that right, so if you do type it wrong it does get a bit messy, but yeah, it has worked, look. So you can see that's our heart-shaped object that's just been created there. Now it is really tiny, it's only 2 by 2 by 4 millimeters at the moment, but we do want to, before we go any further, want to change a couple of other values here. So there are these values U and V. Now if we look in the help window, U we're leaving at 0. U max, we're going to change it, the upper boundary, down to 3.14. Now it doesn't actually have any effect as such, that one, from what you can see. If I change it down to 1, let's see what difference it makes. Now you can see that part of the object has disappeared, quite a big chunk in fact. Okay, now what this value is, 3.14, from back in school days when you did trigonometry, 3.14 is pi, as in area of a circle, pi r squared. So that's what the 3.14 is. And as you can see, if we go smaller than 3.14, part of the object is missing, and that's just how these functions work. Now Vsteps, we're going to change that down to 24. Now the effect of that is that it's changing the number of faces going around here. So if I keep going down, look, yeah, the number of faces going around in this direction, not around the object itself, but around here, is only 4 faces now. So you can make it smoother, in other words with a lot of faces, or you can make it chunky depending upon what value you select for here. So it's still quite chunky at 24. If we wanted it rounded off, we'd have to go really large. Okay, and the downside to that is the number of faces up here increases, so file size increases, but you get a smoother surface finish. I'm going to leave it at 24 because I don't want particularly big file sizes. Vmin, we're going to leave that at 0, and Vmax we're also going to set it at 3.14, and that's the pi again. Okay, so we're using pi here, and that's sort of smoothed it out a little bit as well, because we've got Vsteps 128. Now if we change this down to say 12, let's see what happens if we do 12. You can see it's really chunky. So the V step is going around the object. So 12 means that if we count them, there's 1, 2, 3, and going around, there are 12 faces going around the object. So if we set this at 24, we've still got a relatively chunky object. If we set this at 100, you'll see that the surface does smooth off. There's a lot more faces. There's 100 faces going around the object. So that's what those values do. So 24 is what we're going to set it to in this instance. We're going to just tick this one as well, just because it says so in the help menu. I can't remember exactly what that does. Okay, so there's our object now. So we've changed all of those parameters. So what we want to do now is we want to scale this thing up. As you can see at the moment, if we zoom right back out, it's nothing like the size of the finished one. So we're going to scale it up, and to scale in FluidDesigner, we press S on the keyboard, and I could drag the mouse to scale it up, but in this instance I'm going to type in 100. That looks like it's too big, 100. Looks like we need to reset that value. I'm going to scale it up. I'll do it 50. Let's see what, whoops, where has it gone? Try again. Just press escape to come out of that. So scale it up. Let's scale it up 50. Okay, 50 is what it needs to be scaled up to. Oh, it does say 50 in the help window. Actually, I was looking at the 100 here. So that's scaled it up by a factor of 50. That's what I want to do. And that gives us our values over here for our X and Y and Z values. Now whenever you scale in FluidDesigner, you must always do Control A and apply the scale. Now the only difference between these two objects now is that this one's just been rotated. So it's just been rotated, that's all. Just so when it was displayed on the screen initially, you could see what the object looked like. That's not important, that's not going to affect the way it prints. Okay, now if we zoom in on this object over here, this object has got no thickness on this back side here. Okay, so we do need to apply a solidify modifier to this to thicken it up. So if we go to the properties window and go to add modifier and solidify modifier, and we're going to set a thickness of 1 to 3 millimeters, and so you can see it's adding some thickness there, and I'm just going to offset it to be +1. Yeah, Okay, so I've just thickened this up at the back, otherwise we're not going to be able to get that back surface to actually print. Okay, now to apply this modifier we need to go to Tools, Object Tools, and convert it to a mesh. Now we'll save this now, so we'll delete the original, so X to delete. The one that we've created in today's lesson, what we're going to do is we're going to go to File and Save As, and we just need to go up through the menu system there, go to My Projects, Objet Dart, and save lesson 09 as Heart. Now we can't print Blender files, so we need to go to File and export it as a wavefront object to the desktop as Heart object. And then if we go to Netfab, let's just see what happens. If we go to Project and Open and Desktop 09 Heart object, and so there's our object. So we need to go to Extras and repair the part, and Netfab has had a look at that, and oh yeah, things are looking pretty good here. Sometimes with these parametric equations things can look very strange, but we've got no border edge problems or orientation or holes in this instance, so we just run automatic repair and execute it and apply the repair and remove the old part. Yep, so that's actually done its job. So there's our object. Now, you know, to be honest, this is pretty big object and printing it would be quite expensive, but you could always scale it down. But what we need to do now is to save this, so we go to Part, Export Part as a wavefront object, export it to the desktop, and that's the repaired file. That's the file that could be sent to the printer. Okay. Now, in terms of parametric equations, if you go to our website at fluiddesigner.co.uk, and if you go to the help menu there on our website, and if you go down to the bottom of it, so if you click on Z, or you can just scroll right down to the bottom, we've got a link to ZMath surface, okay, which you probably have come across in some of the other lessons that we've produced. But the one you're looking for here is the XYZ math functions. And if you click on this one here, XYZ math functions at mathcurve.com. Now mathcurve.com is a French website, and if you just type www.mathcurve.com, what you'll get is a French website, everything in French. But if you click on the link that we've just created for you there, it goes to Google Translate and you can make some sense of it. I mean, if you're a fluent French speaker, you've no problem, you can just go to the original mathcurve.com website. But if you're like me and you speak English and know very little French, you're better off going to this website. Now, there are lots and lots and lots of examples on here. You'll see Bezier, for example, Bezier curve. So here's the mathematics behind the Bezier curve. Now, you know, it is true to say that not all of these are easy to follow, not all of these you can use, but there is an enormous number of equations on this website and shapes which you can actually create. So this is the one that we've very similar to what we've created today, and it comes under Klein bottle. I'm not certain whether this is exactly the equation that we've used today, but these are some of the objects that you can create using the Klein bottle function. And if you scroll down, X, Y and Z, ignore this bit at the bottom. Oh sorry, no, it's this is what you want, X, Y and Z. These are the functions that you can enter. Now in terms of using them in FluidDesigner, you do need to use U's and V's. Some of the other equations that are on this mathcurve.com website list things, I don't know exactly where, I probably won't be able to find one. Don't always list them as U's and V's equations, and some of them don't all list parametric equations. So you've just got to sort of play around on this website if you're interested in trying to come up with some unusual shapes. To be honest, I haven't used this website that much, but there is an awful lot of information there, and it's well worth knowing about if you're interested in trying to produce unusual shapes. So that's the end of today's lesson. We've showed you how you can create a heart-shaped object using parametric equations. Okay, so that's the end of this lesson. Thank you.